there. Okay, so good afternoon, everyone. Welcome to this March mini school. Yeah, I'm very happy to have Dr. Kishan Dayaram from here, yeah, to present today. Kishan is a postdoc here in Stellenbosch, but he did his PhD at University of Johannesburg. And he will give us a gentle introduction to ZX calculus. And I'm very happy to see that we don't have only the usual quantum computing suspects in the room, but also some guests from mathematics, which is very good. And I think Donovan, someone just knocked at the door. I will share the screen and then ask do that. How do I do that? View here. Sorry, view, enter full screen, and
ZX calculus.
okay, we are back, and we need to share again. Okay, that's perfect. Yeah.
Okay. So I'm going to be talking about an introduction to the graphical language of ZX calculus. Firstly, what is ZX calculus? It's a diagrammatic way to represent processes, and these diagrams may be interpreted
This connects again on the plan.
Sorry?
This connects again on the.
Yeah, let's see. Okay. Kishan, sorry.
Okay.
Yeah. Maybe you want to start again.
Yeah, so okay, so just to recap that ZX calculus is a diagrammatic way to represent quantum processes, and we may interpret these diagrams in a well-defined as linear maps in Hilbert spaces in a well-defined way. And the ZX calculus gives us rules or axioms for equalities between different diagrams. But there are alternate ways to look at this. They may also be considered as simply rewriting systems, so labeled graph and rewriting rules for these graphs. Or we may view them as string diagrams in a suitable category. And the equalities of diagrams then follows from equalities of string diagrams based on the properties of the category, such as Frobenius structure, Hopf algebra, abelian group structure, and so on. And I'm going to speak a bit more about this later on. So why should we care about ZX calculus? So firstly, the inspiration is from quantum computing. Quantum computing exploits quantum effects for algorithms to obtain an advantage over classical computing algorithms. And namely, we have these three important examples: factorization of numbers into prime numbers, simulating physical systems in chemistry, for example. How is this different from classical computing? Just to recall that for classical computing, we use bits, which the state can be either 0 or 1. We have logical gates. Some examples are negation and an OR gates. And it actually turns out that any logic gate can be formed from some combination of this. So we term this a universal set of gates. To reason about classical computing, we represent abstract function, and we allow to build certain expressions with variables. So how
Okay, we are back. We are back. We are back. Yeah. I don't know what happens today.
Well, I need some sort of software to those files.
it's just PDF. Should I continue?
Yeah.
Okay. So we said that in quantum computing, we use qubits or quantum bits. States of our qubits are taken as unit vectors in the complex number squared. And for n qubits, we're going to have a 2 to the n dimensional Hilbert space. Calculations involving linear maps in such a Hilbert space becomes challenging due to the large dimension when you have enough qubits. So we look for alternate ways to simplify quantum computing. And namely, we look at a diagrammatic approach. Diagrammatic approaches is not new. In physics, they appear as Feynman diagrams for particles. We also have Penrose negative dimensional tensor diagrams as shown in the picture here. We have proof nets used in logic. We have geometry of tensor calculus by Giral and Street, and an example is given here. And just to remark that in this bottom example here, it is also an example of a string diagram, which we will make use of later on in this talk. And we also have trace monoidal category diagrams, and lastly, string diagrams for lambda calculus. Now, this is important as lambda calculus was used to describe classical computation, and we can also use string diagrams to reason about lambda calculus. So before moving on, I'm just going to give a short recap on quantum mechanics to make sure that we're all talking about the same thing. So we said states are unit vectors in a complex Hilbert space. We write states using this Dirac-Braket notation for states in our Hilbert space using a ket, and we have elements of the dual space, which are simply linear maps from the Hilbert space to complex numbers, written as follows here. And from this notation, we see how we recover the inner product for the Hilbert space. But we also consider states equivalent up to global phase. So a state is not, we don't consider an element, we consider it as a collection of vectors in our Hilbert space when we allow phase. However, we can write it, we can write a state in this format in the bottom here by multiplying its adjoint bra to get a representation of the state which is independent of its phase. So we are essentially copying it somehow. The idea of copying also becomes important later on. These states of our qubits can be nicely represented on the block sphere. So on our z-axis, we have our z basis 0 and 1. Which is also sometimes called the computational basis. And on our x-axis, we have the minus plus basis. So what are operations or gates we can do on states on qubits or states of our Hilbert space? We can rotate about the z-axis as shown by this diagram here, and it's also represented by the matrix on top. Similar to how we said that negation and an OR gates are a universal set of gates for classical computation, for quantum computation, we also have a universal set of gates, namely rotation about the z-axis, our Hadamard gate, and our controlled NOT gate, and the matrices representing these operations are shown on the slide here. We also have this way of representing quantum circuits. So the lines represent our qubits, and we have the input register and output register. So in this case, there are 4 qubits going in and 4 qubits going out. And we always read these diagrams from bottom to top by convention. So one thing I didn't mention is that in quantum mechanics, it's a postulate that after discrete time steps, your system evolves according to a unitary operator. So all these operations here can be represented by unitary matrices. So we would like to study quantum mechanics using string diagrams, similar to the previous approaches I mentioned. To do that, we first need to know what a category is. So a category C simply is a collection of objects and morphisms. So we have objects and we have arrows between our objects, such that for any 2 composable arrows, so A to B and then B to C, we can get 1 arrow from A to C, which we call G composed with F or G circled F here. We also need to require some sort of associativity, namely that if I have three composable arrows, F, G, and H, as shown in the diagram here, there's two ways to compose to go from A to D. And associativity requires that these two maps be equal. So this top map and bottom map are equal. And lastly, for any object A, we must have an identity morphism going from A to itself, such that when you compose anything with this identity map, the map you started with G and the other way as well. So there are many examples of categories. We have sets and functions, sets and relations. So a relation from a set A to a set B can be considered as an arrow or morphism from A to B. Usual examples, we have groups and group homomorphisms. And then importantly, for quantum mechanics, we have Hilbert spaces and bounded linear maps. Now, what are string diagrams? String diagrams are essentially what I've drawn below. We want to consider morphisms. F from an object A to an object B, we want to draw it graphically in this format. So we want to represent the morphism labeled by a box and the inputs by wires, inputs and outputs by wires, as shown in this diagram. So I think I'm missing a slide, but to do this, we need to recall that in quantum mechanics, that combining two quantum systems in parallel corresponds to taking the tensor product of their state spaces. And hence, in a category before we can talk about string diagrams, we need some notion of tensor product. So this is what we call a monoidal category. So we have data here. So it's essentially a functor. So a map from the category across itself to the category such that it satisfies these properties. So this does look very technical, but essentially what are we doing? We want a way to tensor any two objects and any two maps in our category, such that we have this unit object and I, such that I tensored with any object gives you back that object. But this is only up to isomorphism. And when we talk about tensoring morphisms, so if I have F from A to B and G from X to Y, F tensored with G will be A tensored will go from A tensor X to B tensor Y. We also require some technical conditions involving these diagrams, requiring that these diagrams commute, but I'll explain what this means. So doing that, as we said, we can represent morphisms using these boxes. And when we place things next to each other, we talk about tensoring them. So these three wires going into this box and two wires coming out simply represents the input being C tensor D tensor E, and the output or the codomain being A tensor B. And the function is labeled by J. We can combine these diagrams in different ways. So the bottom picture shows you that we can combine them in sequence to have F composed with G composed with H on the left. We can combine them in parallel, and we can combine two composites in parallel as well. And all those technical diagrams requiring those diagrams to commute simply say that we don't need to insert brackets when we are doing when we are combining such diagrams. Because if you recall, by the definition, to compose two things, we'd have to put brackets. So first compose F and G and then H. But those conditions essentially say that it's unambiguous. So as we said, we need a monoidal identity. So it's an object I in your category such that I tensored any object X gives you back X up to isomorphism. And in the string diagram notation, we don't draw a line or wire for I. And how would we then have string diagrams from map A to I? So we'd have on the left picture here, we'd have psi going from the input A, which is not labeled here, to I. So the output needs to be I, but we said we don't draw I, so there's nothing going out of it. Similarly, we have a map from I to A given by this phi prime here. The input is I, so we don't include anything there, and the output is A. So for Hilbert spaces, it turns out that our states correspond precisely to the maps I to A. For Hilbert spaces, your monoidal identity is simply the complex numbers. So the middle maps here from I to A are simply your states of your Hilbert space. And the maps on the left, A to I, will be maps from your Hilbert space to complex numbers. So these will be elements in your dual Hilbert space or your effects of the quantum system. And the motivation for drawing it in this way is if you rotate these pictures 90 degrees clockwise, you'll notice that it sort of looks like the Dirac-Braquet notation. What happens when you compose an effect with a state, so a map A to I composed with a map from I to A, we simply get a map from I to I, and this is what we take as our scalars. So usually we write scalars as simply one scalar inside a diamond box. Now, what are the sort of things that we want to capture from quantum mechanics? So one of the key features of quantum mechanics is entanglement. So we want to encode it in this language of string diagrams. To do this, we need the notions of dual objects, and this will be denoted by cups and caps in the language of string diagrams. So the definition of dual objects, we have two objects, L and R, in your monoidal category. We say L is left dual to R and R is right dual to L. If we have these morphisms here, we have eta from I to A tensor B and epsilon from A tensor B to I, such that, again, these diagrams commute. But again, we can interpret these diagrams in the language of string diagrams. So these will turn out to mean something. So on the top here, drawn L and R. Remember, they're objects, so we have to draw them as wires. I've indicated direction here simply to keep track of which is the left dual and which is the right dual. However, later on, we'll see that it's usually clear which is the left and which is the right. So in ZX calculus, you don't normally see these arrows showing direction. So we want L to be the left dual and R to be the right dual. What were the requirements? We wanted eta from I to, we want eta from I to A tensor B. And this is what we can think of here. So on the left here, we can consider this as the map eta. Remember, we have nothing going in because the identity we don't draw. And we can see this as a state, so a box here with two lines going out. So that's the map eta on the left, and epsilon similarly on the right. We have the left tensor, the right, going to identity. And again, we can consider a box on the top of this cap here. So I didn't mention this is the diagram on the left in the middle and the diagram on the right in the middle. We call them cups and caps simply because of their shape. And on the right, we're saying that's epsilon. So we are seeing these cups and caps implicitly states and effects. So because these, we define these as dual objects, these technical conditions here on the previous slide that these diagrams commute are simply saying that when we have these two diagrams here, so this cup and cap coming from the middle two diagrams, we are saying that the law says that we can simplify it to this single line here, which is L. And similarly, the dual property says that this cup followed by cap is simply R. So how does this relate to quantum mechanics? This which we are thinking of as a state is going to be thought of as an entangled state or a Bell state. And this is the dual notion of the entangled effects. But looking at this using string diagrams, we can represent any morphism F going from A to B using these things that we call the name and co-name of F. So we know the input of F is A and the output is B. So instead of drawing F as our usual string diagram like that, we the dual of A. So A star we're considering as the dual object to A, and we can represent F as this in this format here, and we call this the name, and the dual diagram on the right we call the co-name. From these name and co-name diagrams, it's easy to see how you can recover the original map F. So F went from A to B. Suppose I started with the co-name, so the diagram on the right on the top is if we simply join a cup to it on the right, the yanking or snake laws, to stretch this out and have simply the map from F from A to B. Now, those constructions with the name and co-name and that snake law allow us to do something very important, namely that when we have these cups and caps, we can slide F along it. And this will be allowed inside our monoidal category with dual objects. So moving back to some quantum mechanics, what is something else? What is another key feature that we want to capture in this language of string diagrams? Quantum mechanics, we have these no-go theorems. So in particular here, we have a no cloning and no deleting theorem, which says that for no cloning, there are no unitary operations D such that D goes from a state to the state tensor itself. D takes this state to the state tensor itself, and this other state phi here to a copy of itself, unless these two states are orthogonal. And similarly, the dual notion is no deleting, which is listed on the bottom here. And how would we capture that? Using the language of category theory and string diagrams, we would need these things called monoids in our monoidal category. So for deleting, we want to take an element, say call it phi, and we want phi tensor phi and an operation going back to phi. So that's what I've represented by delta here. So delta shown on the top here goes from an element. So you can call it A tensor A, and the output is A. And we also have this epsilon here going, which is just a state, and it needs to satisfy some natural laws that we'd expect when we are thinking about deleting states. So just a remark here that these monoid laws can describe any monoidal operation. So a monoidal operation in mathematics is simply an associative binary operation with an identity element, and we can represent it in string diagrams using this language. So a monoid on a set is a map from, on a set X is a map from, we can represent it using a map from X, Cartesian product X to the set X. And this is precisely what we are generalizing here. So instead of listing the algebraic conditions that we want this monoid in this category to form, I've simply listed it using the string diagrams here. So if we want A tensor A to A delete first on the left and then have A going in on the right, it's the same as A going in on the left and deleting on the right first. If I put in the state epsilon and I have A going in on the right and I want to do this deleting operation, I get the identity. And lastly, we can swap the inputs. So the A tensor A, we can swap them around and it will be the same thing as our original operation delta. Now, if I flip everything, so in this previous slide, if I rotate everything by 180 degrees, I get this picture here, which we call the comonoid laws. So the comonoid laws will have this operation on the top from A going to A tensor A, and we'll have this effect epsilon dagger. So I've called these delta dagger and epsilon dagger for a reason, which I'll explain. But essentially, this is simply an operation from A to A tensor A, and this is simply, in effect, A to identity, because there's nothing coming out. Again, these are the exact same laws, just flipped 180 degrees. So this is dual to the previous slide. And this we can think about as cloning. So for cloning, we want to input one state and get the state tensor itself. So this is how we want to generalize cloning of a state. So what were those daggers that I described before? So a dagger category consists of a category and a contravariant functor, so a functor from the opposite category to the category itself. That's identity on objects, and it's an involution on morphisms. So that does sound technical, but all it is a way to get a map in the reverse direction. So if I have a map F from A to B, then F dagger, we need to require that there exists F dagger, a map from B to A, such that when I do this dagger operation twice, I get back the original map F. And furthermore, dagger on identity map is the identity map itself. And for Hilbert spaces, what would be the obvious option for this dagger operation? It's simply the adjoint map for any linear map. So in quantum mechanics, we're able to obtain those no cloning and no deleting theorems. With this generalization, we are also able to have a generalization of in the categorical context using these string diagrams. So we say that a category has uniform deleting if you can, a monoidal category if you have this natural transformation from your objects to the identity object, which is natural in some way. So all it is saying that you can always transform your objects into the empty diagram, because we said I is the empty Y. So unitary E subscript A is said to delete the state small a if we put in the state small a into the operation EA, and we get the empty diagram. So it turns out with this notion of uniform deleting, we get the no deleting theorem in the categorical context, namely that if we had such a deleting, our category must trivialize in some way. So the way it trivializes is that we obtain what's called a preorder. A preorder is simply a category that has at most one morphism between any two objects. And if there is a morphism from A to B, you could define what we naturally think of an order as A is less than equal to B. So using those notions, we get the no deleting theorem that says if a compact category has uniform deleting, then it is a preorder. Now, this term compact category I did not introduce, but all it means is that any object in our category has a dual object. It's a monoidal category, and there's some symmetry with this monoidal operation. So when I cross wires, it must be up to isomorphism the same as the original starting wires. So this is the symmetry allows me to cross wires. And the dual of this no deleting theorem is this no cloning theorem that says if we have a braided monoidal category with duals with uniform copying, then every endomorphism is a scalar multiple of identity. So I'm not going to go too much into detail here, simply to say that you can obtain it simply by looking at what happened in the no deleting case and take the dual of everything. So what happens when we have a monoid and a comonoid? So those two things I described on the same object A. It turns out in Hilbert spaces, this comonoid and monoid interact in a nice way. So suppose we had a monoid given by the fold-in circle and a comonoid by the empty circle operation, then we know it interacts in this way. So if we have this equality between string diagrams, we say that the monoid and comonoid form what's called a Frobenius structure. But something stronger even happens. So this monoid and comonoid satisfy stronger properties, which is termed a bialgebra. So on the top here, we have a monoid operation. So again, the fold-in circle and the comonoid, the empty circle. We can show that for Hilbert spaces, all of these top equations are satisfied. And when furthermore, we are working with the Frobenius structure, we get additionally the bottom equalities as well. So why are those bialgebras and things and Frobenius structures important? Again, we go back to quantum mechanics. In quantum mechanics, observables are given by self-adjoint operators. And we can write it in diagonal form, as we've done on the top. Here, lambda I are your eigenvalues, and the EIs are your eigenvectors. Turns out that our observables correspond precisely to special commutative dagger Frobenius categories. So essentially, combining everything that I've shown you thus far, those structures on an object A correspond to observables in our quantum system. But for observables, we notice something. In quantum mechanics, if you measure an observable A and then B, it's not in general the same as measuring B and then A. So there's this, it doesn't commute in a sense. So we call operators compatible, or they commute if and only if measuring either, it does not matter which one we measure first. And it turns out that they are compatible if and only if they have a common eigenbasis. When they are incompatible as possible, we call them complementary. And this is defined using this property at the bottom here. If you take any eigenvector in the one observable and any eigenvector in the second observable, and you do the inner product, we should get 1 over the square root of D, where D is the dimension of your Hilbert space. So generalizing this notion of complementary into the language of string diagrams, it becomes this equation on the bottom here. So if we call a Frobenius structure complementary, if it satisfies this equation on the bottom here. And we call it strongly complementary if it's a Frobenius structure, a bialgebra, and complementary. So in that case, it satisfies the well-studied mathematical structure of a Hopf algebra. So Hopf algebra, we have an object A with a monoid and comonoid, and we have a map S from A to A, which we call the antipode, satisfying this equality here. And for a strongly complementary observables, sorry, a strongly complementary Frobenius bialgebra, we we obtain the antipode from this diagram on the bottom here. So I don't think it's too hard to see how this equality on the bottom here, from that equality, you can deduce what S is in that case, simply by comparing the two diagrams. Okay, so that was the categorical background, how these equalities arise. But now let's formally see how we can use them to define the ZX calculus. So for the ZX calculus, we are going to have green and red spiders corresponding to your Z and X basis for your states. And why do we use Z and X basis? Exactly because they are strongly complementary. So because they're strongly complementary, we focus with the Z and X basis. And we have these green spiders which correspond to your Z basis. And we have N inputs and M outputs for this diagram on top. And it would correspond to precisely this unitary operator here, described on the left and on the right here. And for your red spider, we have this, again, this unitary operator here, which shows you how to compute it. We said states were operations with no inputs or identity input, and using these red and green spiders, we can recover our X and Z basis. So our Z basis said it corresponds to green spiders. So for the green spiders, the phases 0 and pi recover our basis, our Z basis. And again, the phases 0 and pi for the red spiders recover the X basis. And again, from this, looking at the block sphere as well, it's not hard to see how you can represent the Pauli matrices using spiders. So what rules do we have for ZX calculus? So for these string diagrams, I didn't mention this in the categorical context, but you see we're moving from bottom upwards. So for this top spider fusion property, you can simply write the corresponding maps it corresponds to, and when you compose them, it's not hard to see that the phases are added. So we can represent this using one spider with the phases added. We can also remove loops, and a spider with a single input and output with 0 phase is just our identity map. Again, by the definition of these spiders, it's not hard to deduce. But the equalities coming from the string diagrams is what's important. So on the left here, we have this bialgebra law, which comes from the string diagram that defines the bialgebra. We have this hopping law, this hop law coming from the Hopf algebra structure, and this last equality on the bottom, which is called pi commutes. This again does not come from the string diagrams that I've mentioned before. This is just something that follows from your definition of spiders. So now that these are the rules of ZX calculus, can I use it as a universal way to represent quantum circuits and quantum computation in general? We did say that a universal set of quantum gates is the Hadamard gate, the rotation about the Z-axis, and the controlled NOT gate. The Hadamard gate, we can actually decompose it in terms of Z and X rotations. So just to mention here that when we have one wire going in and one going out, the phase here is simply just a rotation about whichever axis you're considering, corresponding to what color the spider is. So a Hadamard is simply rotation pi over 2 about the Z-axis, pi over 2 about the X-axis, and then pi over 2 about the Z-axis again. And this recovers our Hadamard gate. So we will use this diagram here for Hadamard gates, but we know that it always can be decomposed into red and green spiders. And on the bottom here, if we have a spider and we put a Hadamard gate on each input and output, we can remove all these Hadamard gates and swap the color of the spider. So based on these rules for ZX calculus, we can show that it's universal, because any Z rotation or rotation about the Z axis can be given with this green spider with phase A. Rotation about the X axis is a red spider with phase B, and the control NOT gate is what's shown here. It's a green spider and red spider with no phase and simply a line connecting them. And because we know that rotation about the Z axis, controlled NOT, and Hadamard gates are a universal set of gates for quantum computing, and Hadamard gates can be formed from the top two gates here. We know that any unitary map on n qubits, we can form a ZX calculus term or diagram here, such that the interpretation of the diagram in matrix form is our unitary map that we started with. So ZX calculus is also sound. What does this mean? It means that if I have two diagrams of ZX calculus, two diagrams that I can draw, then if they are equal by the rules of diagram of ZX calculus, so by the rules I just stated, then the representations using unitary matrices must be equal. And to prove this, you need the language of monoidal categories and monoidal functors, and show that from ZX calculus, you can form such a monoidal functor and prove that we get this equality in the Hilbert space. And lastly, and more importantly, a big result was showing that ZX calculus is complete. So if I have D1 and D2 in the ZX calculus, so these are diagrams, and the only phases we are allowing are integer multiples of pi/4, then if their representing unitary matrices are equal, then there must be some way to deduce D1 is equal to D2 using the rules of ZX calculus. And just lastly, I'll end off with an example of how ZX calculus is useful. So I think this is a common exercise in quantum circuits when we have three C0 gates alternating. It actually equals to a swapping operation, and we can prove this using ZX calculus in arguably a shorter way than the standard way to prove this. And the way to prove this is to look at your diagram. I'm not going to explain in detail now. In next week's talk, I'll go through this in more detail, as well as other examples using ZX calculus. But basically, if you look at the top square, you can rewrite it using the bi-algebra law, and then fuse gates, spiders of the same color to obtain the second diagram. From the second diagram, again, you can apply the bi-algebra law, and then lastly, we remove these two wires joining this green and red spider by the Hopf law to get the picture on the right. And this we can see graphically is a swapping operation. And lastly, I'll end off with some references. So the top two are the standard references for ZX calculus. So Picturing Quantum Processes is a textbook, is a self-contained textbook in ZX calculus and related topics. Quantum in Pictures is a simplified way of explaining ZX calculus, and it's even been used to teach high school students about quantum mechanics. And then I've just listed some other resources on quantum mechanics that I've used. And I'll stop there.
Okay, no, thank you very much. There are questions for Kishan. Donovan, are there questions from our, I see there's something in the chat there. Okay. Any questions from our mathematicians here?
Okay.
So what's the setting where there's humanoid and category ones?
Yeah, so it's what I said, the strongly complementary Frobenius dagger, commutative dagger category.
I see. And in this setting, you can model all the quantum gates.
Yeah, so that's precisely.
Any other questions? Menika, all clear?
Yeah. So yeah, so in next week's lecture, I'll go through some more examples using ZX calculus. So practically on circuits. So I'll go through quotation protocol using ZX calculus and a few other examples.
You know, that I think would be very useful.
Okay.
Excellent. Yeah. And did you do all the figures using the picturing quantum software? Or did you do it
No.
yourself?
So a lot
Just
of
cut
it,
and paste?
yeah. So a lot of it was just cut and paste because drawing them is not so simple. Yeah.
Yeah, that's what I thought. Yeah. Okay, excellent. Then if there are no other questions, maybe just a quick advert on Friday afternoon, because Friday is the International Day of Mathematics. Yeah. And Kishan has invited the first guy there, the Bob Cooker, who one of the inventors of statics calculus. Yeah. And will give a colloquium at 4 in the NITheCS. Yeah. So that will be very useful. Yeah. And next Wednesday, we will see some examples in action. Yeah. So between today, Friday, and Wednesday, we should be fit for ZX calculus. Yeah. Sorry, there's a question there. In which category does it live? Yeah.
So ZX calculus, like I mentioned, we start with the monoidal category. Then what additional structure do we require? We require dual objects to exist and some type of symmetry. So we want it to be compact, or sometimes also called compact closed category. And then we want it to be a Frobenius structure, which I've explained here. So your monoids and comonoids interact in a nice way. And then we want it to be strongly complementary, which is being a bialgebra. So these laws in conjunction with the law at the bottom here. And it also needs to be a dagger category. I think I skipped that. So all those conditions combined give you the exact context needed for ZX calculus. And I think the second part is, where do the matrices come from? So for the category of Hilbert spaces, you can represent your unitary transformations by matrices, and that's precisely what I was doing there.
But probably seeing it in action with a very typical example will probably help a lot.
Okay.
Excellent.
So it's a rigid monoidal category. I'm not too familiar with what rigid means, but yeah, maybe I'll look that up and I can confirm next week.
But the spiders are quite flexible. Okay, wonderful. Then thank you very much, Kishan. Thank you very much to everyone. Thank you, you guys. Thank you, the guys online. And, yeah, we will see all of you again next Wednesday. And please come on Friday as well. Yeah, you'll be in the news. Yeah, thank you. Thank you very much.